So we're going to look at velocity and acceleration in terms of x, because sometimes we're not actually interested when something is happening, we're just interested in where it's happening. Let's assume velocity is some function of the displacement. Now, here's the link between acceleration and velocity. It turns out acceleration is the derivative of a half v squared with respect to x. And this is where we've got to be careful with respect to x. Let's prove it. We know it's dv dt, that we know. And that's useful if I want to link velocity and time together. So if I am interested in time, then yes, dv dt is useful. Let's play around with the dv dt. I could rewrite it using implicit differentiation, chain rule, call it whatever you like. dv dx times dx dt, which means it is dv dx times v. So v times dv dx. Now that is useful when I want to link velocity and displacement together. How do we get to the expression that I've written at the top? Well, if I keep going, velocity I could rewrite, because if I differentiate a half v squared with respect to v, I would get v. So I could swap in for v, d dv of a half v squared, and now the dv's, if you like, cancel, and we have our d dx of a half v squared. And that's the other form that sometimes people use when we want to link velocity and displacement together. I personally find the v to v dx more useful, and we'll do some examples and you'll see why. So let's look at this one. We've been given an acceleration formula, but in this case it's in terms of displacement rather than time. We want to find its velocity in terms of x, and we've been given some initial conditions. We know that at x equals 1, the velocity turns out to be 2. Acceleration. Well, we said acceleration was d dx of a half v squared. If I was to integrate both sides, I get a half v squared is 3x minus x squared plus some constant. We can find that constant. They've given us some initial conditions. With x equals 1, v equals 2, sub in. So if I'd forgotten about my constant, in this case I would have got lucky because the constant turned out to be 0. So velocity squared is 6x minus 2x squared, which means velocity is plus or minus the square root of 6x minus 2x squared. Now this is where it's a little bit unusual, because we've got two possibilities for velocity. We're not used to seeing that, but that's because we're used to working with time. Obviously at a particular time there's only one possible velocity it could have. But when you talk about displacement, there are two possible velocities, because you could be there at different times. So at one time you might have a positive velocity and at another time you might have a negative velocity. So it is possible to have plus or minus when we're talking about in terms of displacement. What about though if instead of saying acceleration was d dx of a half v squared, we said it was v to v dx, which as I say is how I would prefer to do it. And the reason I would is I can just separate my variables quite quickly. But now I don't have to worry about the constant because I can do it as a definite integral. So when x equals 1, v is 2, I want to link velocity and displacement together. Now what ends up happening? Well, on the left hand side I'm going to integrate the v, and there's the half v squared. So I get it anyway by doing it this way. But again, I don't have to worry about the constant doing it this way. On the right hand side I've got 3x minus x squared. Okay, let's sub in our values and you can see we end up with the same expression. V squared is 6x minus 2x squared. Interesting point now, when we look at this, things we know. Well, we know velocity squared has to always be positive, or another way of thinking about that is whatever's under the square root sign here has to be positive. That means 6x minus 2x squared is greater than or equal to 0. And if I was to solve that inequality, I would get that x is in between 0 and 3. So that now tells me something about the path of our particle. It's a very boring life. It's just going between 0 and 3. And that's the only places it exists. Let's do this one. Again, acceleration is in terms of displacement. Being given some initial conditions. But this time they actually want us to find it in terms of time. So somehow we want to get time into this question. Acceleration is in terms of x. So I'm going to use v to v dx. If I separate out my variables and sub in the conditions they've given me. X equals 1, velocity was negative root 2. They told me it was in the negative direction. Okay, let's integrate. half v squared on the left hand side, x cubed on the right hand side, substitute in, and I get v squared is 2x cubed, so velocity is plus or minus root 2x cubed. Now it's the next step where we have to make a decision. So remember, I want to find x in terms of t, but that's all right. Velocity is dx to t, but that's when I now have to choose, is it plus the square root or the minus the square root? Because I've got to work with a function, and plus or minus the square root is not a function. Why did I choose that one? Well, it comes back to the initial condition problem. It has to satisfy the initial condition problem. Which one of these two satisfies it? Well, we said, the ones we used right here, when x equals 1, I get an answer of minus root 2. So it's minus root 2 I need to use to solve this problem. Well, let's now do that one. Oh yes, put it into index form, separate the variables, sub in the initial conditions. This time it's time I'm using. So when t equals 0, x was 1, and we can solve this one. Well, that's great. That's t in terms of x, but they asked us to find x in terms of t. And now we need to make x the subject of all this. T plus root 2 will be root 2 on x, and playing around with it, eventually we can come up with an expression. So x is 2 over 2 plus root 2 all squared. This is an interesting one from last year's HSC, and they've given us a diagram. Personally, I didn't like the diagram because I would have preferred to see the forces put on this, and for some reason they put the accelerations on it rather than the forces. Bit weird. Maybe let's just assume it's unit mass and then everything's okay. Just be multiplied by 1. But alright, they've given us the accelerations on it. So subject to the acceleration due to gravity of g and the magnet of 27g x cubed, and they've done the work for us. They've set up the acceleration, so we didn't have to create it by looking at the forces and going, oh well, the resultant force would be this. They've given us the acceleration for this one, and what I can see from this is they have assumed that up is positive. So up is the positive direction. We've got to find this expression for v squared then. Right, they gave me this formula. Acceleration is 27g on x cubed minus g. Acceleration is in terms of displacement. I'll use v to v dx. Separate out my variables. Now, they told me that it started at a displacement of 6, but it was stationary at that point, so velocity is 0. Now, you'll notice I didn't bother writing a half v squared on the left, but what I did was I multiplied the other side by 2, because I'm going to make v squared the subject eventually anyway. So I may as well just multiply by the 2 straight away. So on the other side, I've made that 2g. And then done my integration. Left hand side then is just going to be v squared, which is what I want, and hopefully the right hand side I can now manipulate it, and which I can, into the expression that they wanted. Then we had to find when the object next comes to rest. So initially it was at rest, but then it's going to come to rest at some other point. So essentially, when is velocity equal to 0? That's what we're solving. Alright, we've got a cubic to solve, but fortunately we know one of the solutions to that cubic already, because remember, we know velocity was equal to 0 when the displacement was, what was it, 6, wasn't it? So we know that x minus 6 must be a factor of this. What's the other factor? Well, you can do a polynomial division or use logic, but leading terms times the leading term is 8x squared, constant times the constant gives me 108, so that must be negative 18, and then work out how many x's. Well, at this stage I have minus 18x, but I don't want any x's, therefore the middle term must be minus 3x. And that's just a quadratic, and we can solve quadratics quite easily. Ooh, we actually have 3 solutions. They want the one when it's next comes to rest, and I'm not dealing with time here, I'm dealing with displacement. What I do know about this problem is that displacement has to be greater than 0 because it was above it, and we said it was in the positive direction, so it's going to be the positive answer would be the next time it comes to rest. And bung that into the calculator. They said to 1 decimal place for some reason. Maybe a physics teacher wrote the problem. The exact answer is quite fine, really. But there it is, 1.7 to 1 decimal place. And I suppose I really should have said metres, shouldn't I? I think the unit was metres, wasn't it? Oh, it must have been. Must have been metres. Why must it have been metres? Gravity, and of course we know gravity is measured in metres per second squared, so it must have been metres we were dealing with. So 6A.